Hello, and welcome to another supplemental lecture for my PSYC 440640 class. The class is called Experimental Methods, but for those of you who are enrolled in it, you know it's really a class about mostly univariate statistics, some of which is applicable to experimental designs and methodologies, but some of which could be applied also to non-experimental stuff. Anyway, the purpose of this supplemental lecture is to elaborate on a point that has come up in recent lectures for that class, and that point is the problems associated with statistical hypothesis tests that have low power. If you've paid any amount of attention to the literature on research methods and analyses in psychology over the past many decades, but especially over the last 5 or almost 10 years, you know that this issue of findings associated with studies that have very low power is a big deal for us. It's the source of a lot of concern and a lot of criticism, especially now, but actually dating back for quite a long time if you look carefully in the literature. So anyway, let's run through a simple example of what a low power test might look like, and then talk about some of the problems that such a test might have. So here I have an image that I generated with G-Power, and what it is two distributions: a distribution for the test statistic T under a null hypothesis, that's the null distribution in red, and then under an alternate hypothesis, that's the distribution in dotted blue. And this is it's kind of a silly study because it only included 10 people. It's a fictitious study that I made up, so that's a really small sample size. You can see that with that sample size, or the associated degrees of freedom for a t-test, the critical value for t is about 1.9, and that critical value creates a boundary that divides both the null distribution and the alternate distribution into these different regions. And those regions are useful to think about because they're important for us. One of those regions, the region to the right of the green line in the null distribution, is the cumulative probability under a one-tailed test for type 1 error, that is, for rejecting the null hypothesis when you really shouldn't. That means if you, in a particular test, had a t-statistic that was 2 or 2.5 or 3, you would, based on the criteria of t-critical being 1.9, you would reject the null hypothesis. But it's conceivable that really there is no difference between your groups, or no effect of the variable you're testing. You've created a false positive, or you've indulged in a type 1 error, and that's going to occur over a long run of tests, approximately 5% of the time. That's the alpha level, or the type 1 error rate. The beta level, or it's beta not as in beta as in the regression formula, but beta as in capital B, or type 2 error rate. That's the region to the left of the green line in the dotted distribution. That's the reflects the possibility that your t-statistic was not sufficient to reject the null hypothesis. Maybe the test statistic you observed was 1.5, and so based on your t-critical value, you chose not to reject the null hypothesis. But unbeknownst to you, there really is a difference between groups in the population, or an effect of the variable in the population. And again, unbeknownst to you, you've indulged in a false negative, or a type 2 error. And then just by simple subtraction, power is defined as 1 minus beta, or in this case it's about approximately 0.1, and that's the area to the right of the dotted line to the right of the green line in the dotted distribution. So if you're not making a false negative, you're making a true positive. That means you're correctly rejecting the null hypothesis. You're detecting an effect if an effect is there to be detected. So this is pretty standard post hoc power analysis that you could do in G-Power or similar programs. Obviously there are other ways to conduct power analyses for more complicated statistical tests, and also for different purposes. For instance, if you were trying to plan a study so as to have a large enough sample to give you greater power, or if you're trying to see how big a sample size you might need under different assumptions about your effect size, you could do this a priori. This is just a kind of a simple fictitious example that I dreamt up of a post hoc power analysis for a rather small and, as you can see, rather underpowered study. So this study has very little power. We'd expect over a long run of tests identical to this one, only about 1 time in 10, or a little bit less than that actually, would we detect an effect if such an effect really existed. So that's not so good. This test doesn't have a lot of ability to detect effects even if they're there. So an interesting issue that comes up is what happens if your study has low power but your test statistic is large enough to reject the null hypothesis. If your study has low power but it apparently reveals a significant effect, is that a problem? Now, you or some researchers might argue that this isn't a problem. You might say something like, hey, I found an effect, so I must have had enough power in my study. I've actually literally heard people say this. Someone, maybe it's me, maybe it's someone else, has tried to gently point out, hey, your study had very low power, and the person says, well, I must have had enough power because I've detected a significant effect. Is this a problem? I would argue it could be. It depends especially on how low your power is. So again, let's think about what a significant effect is. A significant effect just occurs when our test statistic is large, and therefore its probability under a null distribution under a distribution associated with the null hypothesis is very low, so we reject the null hypothesis. Now, if we reject the null hypothesis, there are 2 things that could be happening. Or put more simply, there are 2 possibilities. There might be a real effect. That is, there's a real relationship between our predictor and outcome variable, or equivalently, potentially like a real difference between 2 groups if we're doing a t-test. And so in those type of situations, rejecting the null hypothesis was correct. It was the right call. Now, we don't necessarily know that to be the case. Let's just suppose that it's possible that in the population of data there really is a relationship between these variables, or there really is a difference between these groups. So when we rejected the null hypothesis, we got it right. Of course, the other possibility is we created, or we performed pardon me, a type 1 error. So there really isn't a relationship in the full population of data, and so rejecting the null hypothesis was a mistake. Now, part of the problem here is in a low-powered study, it's hard to decide which is more likely. So for instance, the type 1 error rate might be very low, 0.05, so there's a 1 in 20 chance that we have a type 1 error. That's pretty low. But there's also, as we observed in the calculation before, only a 1 in 10 chance that we correctly rejected the null hypothesis. So I guess technically speaking, 0.05 is less than 0.10, but it's still pretty small probabilities. And if someone came up to me and said, gee, my test that I've run, or my analysis that I've run on my data has a 1 in 20 chance of being a false positive, but it's got a 1 in 10 chance of being a true positive, I don't know if I really like that comparison of probabilities and feel all that confident that I could really decide, based on this just one sample and this one set of analyses, which of those 2 possibilities was more likely. Now, contrast that rather bleak situation to the situation you might have in a rather high-powered study. So let's imagine that you have a very large effect size. The distance between the null distribution and the alternate distribution is quite wide, which you can see quite easily here, especially given that it's a one-tailed test. Let's also assume that you ran quite a lot of participants in your study, which in ways that aren't totally obvious to visualize, at least not on a graph scaled like this. That kind of changes the shape of those test statistic sampling distributions. And so suffice it to say that power, the area under the curve to the right of the green line in the dotted distribution, is quite big. Alpha, which is our type 1 error rate, still is small. It stays small at 0.05 because we hold it there. Now we have a kind of a different judgment that we could make. You might come up to me and say something like, well, I ran this study and I found what appears to be an effect. It's statistically significant. The probability of a type 1 error is 1 in 20, but the probability of a true effect, a true positive, is about 8 in 10 or 80 in 100. I might think about those two probabilities and say, wow, it seems somewhat more likely that what you've observed here is a true positive effect than a false positive effect. We can't be absolutely certain, but I think I, and probably most people, would feel somewhat more comfortable making a judgment in this high-powered case versus the previous low-powered case. So again, you or someone in this position might still argue the power of my study was low, but it's still higher than alpha, p equals 0.05, so I think it's more likely that my effect is real. Again, I would argue that this is still a problem. Again, the distinction between alpha of 0.05 and power of 0.10 is pretty narrow in my mind. But what's maybe even a bigger problem is it kind of depends on how you got to that test statistic that has a p-value that's lower than p equals 0.05. How you got to that sufficiently large test statistic with a sufficiently low probability that you rejected the null hypothesis. If you ran lots of different versions of the study that you were doing, and the effects in the first few studies weren't significant, so you made some slight changes in your protocol, or maybe you gathered a few extra participants and you repeated, and then you tweaked and repeated, and you tweaked and repeated, and eventually by the fourth iteration of your study, or the fifth or the nth iteration of your study, you then get a significant effect. P test statistic is large enough that p is less than 0.05. And then you decide to interpret the results, you may have put yourself in kind of a tricky situation, whether you realize it or not. You may have unwittingly capitalized on the inflation of type 1 error rate. I didn't include the equation here, but it's a pretty simple one to demonstrate that the more times you run a test at a fixed level of alpha, the more the probability of a false positive across that whole family of tests increases. This is sometimes called inflation of family-wise error rate or inflation of type 1 error rate. And you can see this in a sense depicted in this clever cartoon by XKCD, which I highly recommend. If you don't follow XKCD, you should. The person says, I'm a psychic. His friend says, there's no such thing. Okay, think of a number between 1 and 100. Okay, 43. Holy shit. I try not to let it affect my life too much. Wait, I can't believe this. Don't worry about it. Forget I said anything, but let's go to a movie. This trick only works 1% of the time, but when it does, it's totally worth it. You, in this scenario that I just previously described, might be like this. You keep on kind of tweaking and fiddling with your study and iterating and iterating and iterating, and eventually you get what appears to be a significant effect, and you just got lucky. It could be the case that in the population of data there's no difference between the two groups that you're testing, or no relationship between the predictor and the outcome variable that you're testing, but over a long number of times, especially with certain tweaks that I've described, you increase the chances of finding, in quotes, an apparent significant effect. So that's one problem. Another problem is if your study had a lot of predictor variables in it, meaning that you tested the effect of a lot of different independent or predictor variables on your outcome variable or your dependent variable, and there were no significant effects for most of those predictions, which you then ignored or put in the real or figurative file drawer of your desk. But then maybe for one of those predictor variables there was a significant effect, and that's the one that you really focused on and you wrote up your manuscript or your poster about. So predictor 1, no significant effect. Predictor 2, no significant effect, so on and so on. And by the time you get to predictor 4 or predictor 5 or predictor n, you get lucky and p is less than 0.05, and that's the one that you talk about and focus on, ignoring all those previously non-significant, at least apparently non-significant analyses. If you do this, we might describe your analytic approach as a bit of a fishing expedition. You keep on casting the line and eventually you catch something. I suppose the difference is, and I don't fish, but if I was, or if I did fish, the difference is in a real fishing expedition, you can be sure that you actually caught a fish. In a data analytic fishing expedition, you can't be really sure you caught a fish, at least not in the sense of detecting an effect which is true in the population of data. Once again, XKCD has a nice description, a nice comic that kind of describes this. So here we have a citizen, a person run up and with the claim that jelly beans cause acne, and the other person says, "Scientists, investigate this." And the scientists say, "We found no link between jelly beans and acne. P is greater than 0.05. And the first person says, "That settles it." But the second says, "I hear it's only for a certain color. Scientists, get back to work." And the scientists go on and explore the effects of purple jelly beans and brown and pink and blue and so on jelly beans on cancer. And they find no effect, no effect, no effect. And somewhere down the line, they test the effect of green jelly beans on cancer, and for that analysis, P is less than 0.05, and they perhaps, and certainly the other people who read about this, are surprised, and they say, "Whoa." By the end of the day, the press release from the university has been picked up by news sources, and we have a headline that says, "Green jelly beans are linked to acne," or cancer, or whatever I was saying before, with 95% confidence, and a breathless summary saying only 5% chance by coincidence. This is problematic, and in such a case, it's possible, of course, that there is a real population level relationship between green jelly beans and acne. But it's also possible that this apparent effect, which we've observed in a sample of data, is just a false positive. Why does this happen? Well, there are different ways of explaining this. The things I like to focus on are first measurement error. Measurement error occurs when the scores that you for something you're measuring vary across repeated measurements. And measurement error is a phenomenon that is ubiquitous in science. Even in so-called hard sciences like physics and chemistry, people who work in those areas will tell you, if you measure something, you measure it again, you never get precisely the same numbers. Out to some decimal place, there'll be slight differences. And in psychology and the other behavioral sciences, this is probably even more of a problem. If you measure depression among different people, you'll get different measurements. And if you measure depression among in the same person repeatedly over time, you get different measurements. If that phenomenon is in fact changing, and even if it isn't. And the point here is that sometimes those measurements on some trials or in some analyses will go in the quote significant direction, giving the sense that there's a relationship between two variables or a difference between two groups. Another thing that can contribute to these false positives, or the incidence of false positives, is sampling error. If we repeatedly sample from the same population, each time computing a test statistic, like a t or an f or a chi-square or whatever, there's always a chance that sometime those statistics will go in the positive direction, or in the direction that seems significant, just by chance. There are I don't have a good image for it in this supplemental lecture, but I think I do in a previous one that I put up. But if you were to repeatedly sample from a population and perform calculate a statistic, you would have a sampling distribution for that statistic. Sometimes the values would be rather high, sometimes they'd be rather low. Hopefully, if your sample sizes are big enough, they'll tend to clump in the middle and the overall distribution will look normal in shape. But the fact is, the values will vary, and this is sometimes called sampling error. So measurement error and sampling error are related to the idea of unreliability. An effect will be inconsistent across time and across sample. Measurement error and sampling error can also be thought of as related to invalidity. They can lead to inaccurate measurements or inaccurate estimation of parameters. If we want to get a little bit fussy about this, we could even try and make the argument that measurement error leads to problems with internal invalidity, or problems of internal validity, internal invalidity. An effect doesn't reflect a real causal relationship that we're studying. We could argue that sampling error relates to, or can be closely related to, external invalidity. An effect that we observe in our sample won't tend to generalize across a population that we're hoping to make inferences about. An idea that's related to this or kind of emerges from this is the idea of overfitting a model. And by this I mean anytime we do analyses, at least the type of analyses that I tend to do and I teach about in my class, we're almost always making a model, like a regression that's trying to describe the data that we have in our data set, and we're sometimes comparing one version of that model to another version of that model, doing a comparison approach. The model that we make can be overfitted to our sample if it works in that sample but doesn't work or doesn't replicate across other samples. So we might have a situation if we've fiddled a lot with our measurements, or if we've fiddled a lot with our sample size, adding additional people to our sample, trimming out people who we think don't exactly fit our expectations, that we could arrive at a sample which is finely tuned, whether we realize it or not, to suggest an effect between a predictor variable and an outcome variable. That's great in a sense because it sort of looks like in our sample that the predictor variable, group membership or some independent variable, is predictive of the outcome variable. But it may very well be the case that if we were to go out and gather a new sample of people, that we wouldn't see that same effect at all. It might not replicate at all, and we might say, well, gee, this effect, if it exists at all, doesn't generalize to the population. Or it might, the effect might show up in another sample, but it wouldn't be as large. The effect size would be smaller. This is sometimes called shrinkage, or more recently, the somewhat controversial and discredited science journalist Jonah Lehrer called this the decline effect. So basically an observed effect size in one sample, when it's observed in another sample, seems smaller, maybe even to the point of being trivially small. So far the points I'm trying to make is that there are ways in which we can tend to fiddle with our analyses or fiddle with our sampling protocol that make it likely or more likely that we can find an apparent significant effect in our research. These problems exist in all research, at least all research that uses the null hypothesis significance testing approach that we often use. These problems, though, are worse when we have low-powered research, and I'll sort of talk about that in just a few more slides. But before I get there, I should just note that these different sort of tricks or techniques, whether they're consciously attempted or not, have been given different names in recent years. They're sometimes called questionable research practices, or QRPs. These are just things, practices that tend to increase the likelihood of, quote, finding significance. I'm putting that in quotes there to suggest the kind of suspicion that we might hold results from analyses that use QRPs in. Things like running multiple studies until you get an effect which seems significant, repeating and tweaking and adding participants until the effect is significant, then stopping analyses or stopping recruitment. Testing multiple predictor, or for that matter outcome variables, in separate analyses, and ignoring or filing away in the file drawer null findings or non-significant findings, and focusing on only significant findings. These two, over a set of studies, will tend to increase the likelihood of finding results which appear to be statistically significant. So again, questionable research practices have been one name given to them. A somewhat more critical name, I suppose, is p-hacking. People are sort of hacking their data sets so as to achieve p-values, probability values, type 1 error probability values that are lower than 0.05. Simonson and colleagues in 2011 published a really good paper called False Positive Psychology, where they showed that by fiddling with data sets or with analyses in these ways, and these are very commonly used ways, other research has demonstrated that people tend to do this stuff, you can get pretty much any effect to seem significant. And they did some funny things in that paper, like showing that when people listen to the Beatles song When I'm 64, as compared to some other control condition, the people in the Beatles condition aged more rapidly, which obviously seems impossible, at least as we understand time to progress in this universe, but it was statistically significant. And there are other more extreme examples have been found in the literature of people who have at least apparently engaged in these practices and found rather incredible findings that appear to be statistically significant. a kind of a worst case scenario in my mind, and I'm not the only one who thinks this. In fact, the field, there's an emerging field of what's sometimes called meta research, which attempts to kind of analyze the ways in which research is done. This meta research field has really become, at least parts of it, some authors have become very critical of these worst case scenarios. But as I see it, the worst case scenario is you have a paper that includes multiple studies, all of which are rather low in power, and some of them are called conceptual replication. So in the first study that the authors report, they find some sort of an effect, and then they repeat the analysis with a new sample and try to manipulate the predictor variable in some other way, or try and observe a relationship between the predictor and the outcome variable in some other way that's maybe loosely or not so loosely associated. And they say, well, we've conceptually replicated the effect 2 times or 4 times or 12 times. In many fields, this approach has been popular. Certainly the field of experimental social psychology for years, and maybe even still now, tends to do this a lot. And authors who work in that field will say, well, I had 12 studies in my paper and they all showed this effect. And the argument that's being made there, explicitly or implicitly, is there's some sort of majority evidence that's being reported. Like, here's this huge weight of evidence. It all suggests that some effect, some priming effect, some depletion effect, whatever, is real. The problem is that if all of those studies are rather low in power, and if they're all positive, that is, they all claim to show statistically significant results, we actually should be very dubious about them, not very persuaded by them. We should be very skeptical, I suppose, is the opposite. And the reason is that finding a significant effect in a single low power study is unlikely, by math and by definition. We have a study in which we wouldn't expect to see a real finding show up. The fact that a researcher can bundle together 2 or 4 or 8 or 12 studies, all of which are low powered and all of which sort of go in the statistically significant direction, is even more unlikely than a single study that's low powered going in the statistically significant direction. The author Uri Shimek in 2012 published a paper called The Ironic Effect of Positive Findings, I think. It's a really good paper, and it's funny, 2012 doesn't seem like that long ago, but this whole field, Shimek and Simonson and a number of other authors have really, Francis, have picked up the torch and really developed a lot of very interesting techniques for sniffing out apparently unusual or ironic or suspicious patterns of apparently replicated findings. And their work and the work of others has really highlighted how fields like experimental social psychology, and perhaps like others, which tend to traffic in large bundles of low-powered studies, are actually very suspicious, not very, or suspicion-inspiring, not very confidence-inspiring. So these, again, my sense, I guess I'm rambling here, is that these are kind of worst-case scenarios in terms of the credibility of their work. Now, to be clear, replication is not a bad thing, but what I think many authors these days would like is something more akin to real replication or direct replication. This is where a researcher finds evidence, at least apparent evidence of an effect in a particular study, and then he or she, alone or with colleagues, gathers a new sample of data and repeats the study, the same manipulations, the same measurements as best as possible without varying things conceptually at all, and sees whether the effect shows up again in this new sample repeated in exactly the same way, or analyzed and tested and analyzed in exactly the same way, especially if the replication attempt has sufficient statistical power to detect an effect that's really there. It's certainly possible, or I would argue even acceptable, for researchers to use low-powered research maybe at an initial or kind of piloting phase of their work, where they're just trying to see if they can get their laboratory to work properly or their measurements to be recording properly. That's probably okay, at least as far as I'm concerned. But the real proof, if we want to call it that, comes when an effect can be replicated in an independent study that has sufficient statistical power to detect an effect, if such an effect even exists. I guess I've kind of danced around this this topic a little bit already, but much of this stuff ties into what has been in recent years called the replicability crisis in psychology. The crisis is simply that many major findings don't appear to be replicable. They don't appear to show up or appear when researchers try to test them again. And I've already kind of picked on experimental social psychology. I suppose that's a bit mean or unfair. This is a field which has had huge trouble with this problem recently, though they're not alone. I mean, there are areas of neuroscience, there are areas of medicine and clinical trials, especially medical trials for things like drugs, which have some of the same problems. They're run using very low power. Non-significant or null findings are tossed out or ignored or minimized or hidden from the publication process, which creates a very distorted literature which tends to suggest that particular priming effects or depletion effects in the area of social psychology exist, or particular drugs are effective in the case of medical research when they're not. Sometimes it's been found that major findings just don't replicate at all. Sometimes it's found, like I suggested before, that these findings do replicate, but their effects are much smaller. Again, evidence of shrinkage or overfitting the model, or a decline effect, if you want to call it that. To be clear, it's you might at this point in this little supplemental lecture be thinking to yourself, so low-powered studies are really terrible, right? At best they have a hard time finding significant effects, and at worst they can lead us to really flawed interpretations or flawed inferences about the existence of effects in the population. I don't want to paint too dire a picture. I would argue that low-powered studies aren't really that bad. It just depends on how many of them you do and how you aggregate the results of your studies. Again, the worst case scenario is when someone runs a series of low-powered studies and either tweaks the methodology on in an ongoing basis so as to fiddle with sampling, or so as to fiddle with measurement, and so as to kind of p-hack their way to p less than 0.05, and in addition to that maybe fails to report or deliberately hides null findings. That's bad. That creates a distorted literature which can lead to all sorts of really significant problems in interpreting results. What's not bad, though, is when people run a series of studies which may have low power, but they report their results and they aggregate them using meta-analytic techniques. Meta-analysis is a way, or a sort of a series of techniques that are useful for combining the results of different studies so as to more accurately estimate parameters, like the effect of one predictor variable on an outcome variable, or equivalently we could say maybe the difference between two groups in the population. This is two figures here, of course. The one on the left is showing 3 different studies that are run on some sort of an effect, and you could imagine that if these are reported independently of one another, you might get the impression that, well, the first study had a null effect, so maybe that's not even reported at all in the literature. The author who does that study doesn't publish it at all. The next 2 studies are reported, and maybe you have the sense that, like, well, 2 out of 3 is kind of like 2 votes in favor of the effect existing, 1 vote if you're aware of it existing, 1 vote if it's ever published goes against the effect existing. Maybe that suggests to us that whatever is being measured here kind of exists. That's not really that interesting to us. It's problematic. A better approach might be to take all 3 of those findings and combine them so as to be able to narrow the estimate, or narrow the margin of error around the estimate of whatever it is we're studying, whether it's an effect size that describes the difference between 2 groups, or the predictive effect of one variable on another. You can see on the right figure There's just study 1 by itself, has a null finding. Study 2 is run and is meta-analytically combined with study 1, which is sort of like averaging the two of them together. And now it appears that the effect is significant. And also we have a rather tight estimation of whatever the parameter is. You know, in this case, it's a must be like a Cohen's d for the difference between two groups. Study number 3 is run. And we get an even tighter estimation. And you can see that over time we're getting a kind of a narrowing of our focus and greater precision, greater confidence in whatever effect it is we're measuring. So bottom line is, low-powered studies can be part of this story. They just can't be the only part of the story. And they have to be kind of an honest part of the story. Honest in the sense that when they're significant, they're reported. When they're not significant, they're reported. And people refrain from p-hacking and questionable research practices, and when a literature exists, then it is carefully meta-analyzed. And meta-analysis is complicated, and there are some controversies as to how to do it properly, but low-powered studies can be part of it, they just can't be the whole story. Anyway, that got a little bit rambly towards the end of this supplemental lecture, but I hope it helped you to understand some of the problems associated with interpreting significant effects, especially from single studies, when those studies have low power. So if you've made it this far, congratulations. Take a rest, pour yourself a cup of tea or a cup of coffee or whatever to stimulate your mind, and let this all sink in. And if you have questions for me, let me know. I'd be happy to explain this to you in the comments section, or perhaps face-to-face if you're taking my class. Okay, cheers, goodbye.